Hi everybody, welcome back to the Feynman technique. So today we'd like to develop a generalized expression for this integral. All right, so we want to derive a generalized expression. So instead of just evaluating it directly, we can solve it more easily for specific powers of 2. For instance, t is equal to 2 or 4 or 8, and then look for a pattern that we can extend to any continuous t. All right. So the first thing we're going to recognize is that this is true. This is just, this is just true. This integral is equal to that. All right, that means we should be able to plug in any value, real or complex, into this, and it will be valid. So we're going to choose a is equal to e to the I pi over 4, meaning a squared is equal to I. So now our integral on the left transforms into this, integral 0 to infinity of 1 over x squared plus I. And on the left hand side, we have, or I'm sorry, on the right hand side, we have this. All right. So, first thing, we rewrite our complex integral right here just by multiplying upstairs and downstairs by the conjugate, and then splitting the real and imaginary parts. Now, this is the part we're interested in, so we will match it with its imaginary part on the right-hand side, which is this. And eventually, that leads us here. And then, of course, you'll notice the negative signs will cancel out. So I sub 4, or I of 4, is equal to pi over 2 sine pi over 4. Don't forget our original I was in terms of t. So I of t was our original target integral. And now we've shown the special case where I of 4, for I of 4. So we know that. All right, now let's take a look at this integral. You notice this is kind of similar to the integral we got in our last step, except I'm replacing a, or 1, with an a to the 4th, and then making the substitution x is equal to au, giving us this, then giving us this, and finally, this is simply a to the negative 3 times our I of 4. So now let's plug in a to the 4th is equal to I. So we need a to equal e to the I pi over 8. And if we do the same tricks we did in the last step, we will see that this is true. And then we multiply top and bottom by the conjugate again. Again, like I said, we do the exact same thing that we did in the last step to get I of 8. And I of 8 is going to be this. And you should be noticing a pattern now. I of 16 is going to be this. So now we have established a pattern for our target integral evaluated at powers of 2 to the n. All right, and this is the pattern right here, and we'll state it more formally in the next step. You'll notice that this angle right here, the denominator is always increasing by a power of 2. And the numerator is always the denominator divided by 2, then minus 1, then times pi. So this is our angle. This is always our angle right here. So our I evaluated at 2 to the n is equal to, well, we have this pi over 2 term. That's always there. And then we just do out the infinite product. You'll notice this is eventually, if we continue it out indefinitely, this will turn into an infinite product. The next term would be sine of, let's see, so 15 over 32. That would be the next term. And we can express it formally like this. This is the pattern for any n. All right. So now we'll notice that this is just sine of pi over 2 minus an angle, which is just cosine of that same angle. So we'll rewrite it in terms of cosines. Okay, now we're going to set this aside. Our I sub 2n is equal to this. So what we're going to do now is use a different technique to show what this is equal to. And therefore, we will have shown what I sub 2n is equal to. All right, so where we're going to start is just the double angle identity. Or I guess this is technically this is a double angle identity on sine x. So sine x is equal to, well, the double identity applied to x over 2. So it's 2 sine x over 2 cosine x over 2. Well, if we use sine x over 2 is equal to that, and then we use the identity for sine x, which is 2 sine x over 2 cosine x over 2, but replace our sine x over 2 with what it is, which is this, then we end up with this, which is just 4 and times sine x over 4 cosine x over 4 and then cosine x over 2. All right, we'll do the same thing again. We'll use that sine of x over 4 is equal to this, and we'll replace it in our previous definition. So we have now sine x is equal to, well, in our previous one, we had it was equal to 4 times sine of x over 4. But we're going to replace our sine x over 4 with this representation of it. So we have this. So now you'll see that sine x is just equal to 8 times all this. And you'll notice we're always going to have one sine term followed by a product of cosine terms. So after n steps, this is what you end up with. Go ahead and take a look at the pattern, work it out for yourself, but this is the pattern formally stated. So this is, this should jog your memory a little bit. This should remind you of something. This is very similar to our I of 2n. Very, very similar. So what we're going to do next is just divide by this term right here. And now it looks even more similar. All right, how are we going to get it exact though? Well, let's see. Our original I sub 2 to the n did not have any variables in it. So we're going to need to evaluate this at a specific point. And the point we're going to choose is pi over 2. And not only that, but we're also going to bring n to n minus 1. So let's take a look at what that is going to do. If we let x equal pi over 2, well, that's self-explanatory. We literally let x equal pi over 2. Okay, and then what does it mean when we say bring n to n minus 1? Well, what that means is we're going to basically take this n and make it an n minus 1. And in other words, we're subtracting 1 from the index on this entire product. But what that means is that we need to add 1 to all of our k values inside the product. I hope that makes sense why. So that's what that means to bring n to n minus 1. All right, so if we do that, this is what we end up with. So this is our I. This is our I in terms of 2 to the n. So what we've really done is, I'm going to go all the way back to the beginning now. We have a general form for this integral, except where our t is 2 to the n. Now, I'm not going to get into the details of why you can analytically continue that to any continuous t, but it works. You can just let t equal 2 to the n and replace it on both sides. And finally, we have our I sub t is equal to this. A lot of formulas stated as pi over t times the cosecant of pi over t, but we will leave it in this form. So in other words, I should have written the original integral here just to really nicely wrap it up, but I didn't. But here's our original integral right here. Integral 0 to infinity of 1 over x to the t plus 1 dx, and that evaluates to this. I hope the explanation was clear, because I think it's really important to understand where formulas come from, so it's not just a huge mystery. So this formula it'll allow you to evaluate any integral like this. And a lot of integrals can be decomposed into forms like this. So very, very powerful formula. I hope you enjoyed that, and we'll see you next time.